All right, let's get into it. Today, we're tackling one of the biggest questions in AI right now. How in the world do developers train these absolutely gigantic language models without a supercomputer? I mean, we're talking about making custom AI a reality for everyone, not just the big tech giants. So, how do they pull it off?
So let's put you in the driver's seat. Imagine you've got this super smart general purpose AI. It's great, but you need it to be an expert, a specialist. How do you actually do that? How do you perform that kind of delicate surgery on a model with billions, and I mean billions of parameters, all on hardware that you can actually get your hands on? Well, turns out it's this constant, brutal tug of war. Every single choice you make pulls on one of three ropes: quality, speed, and memory. You obviously want the best possible model. You want it trained, yesterday. And, critically, it has to actually fit in your GPU's memory. The catch? You almost never get all three at the same time. Something's got to give. But, and this is the cool part, engineers have come up with some incredibly clever tricks to manage this chaos. Think of it like a toolkit with 4 special levers they can pull. These levers help them balance the trade-offs and, honestly, make what seems impossible totally possible. These are kind of the secret weapons of efficient AI training. So let's just quickly set the stage here. We're talking about the AI training dilemma. Why is it so ridiculously hard to fit these models into memory in the first place? Let's break it down. Okay, so now for the solution. The 4 optimization levers. This is really the engineer's toolkit for making all of this work. All right, here they are. These are the 4 levers that determine whether your training run, well, even starts. We've got mixed precision, batch size and its buddy gradient accumulation, then gradient checkpointing, and finally, quantization. Getting a handle on these is how you win that tug of war. First up, precision and batching. This is all about smarter math and smarter data. Okay, so let's talk mixed precision. My default in AI model is basically a giant pile of super precise numbers. Think of them as 32-bit numbers. They're incredibly accurate, but they are also memory hogs. They take up a ton of space. Mixed precision is this fantastic trick where we say, hey, for most of our calculations, let's use a smaller 16-bit format. Just that one change cuts your memory usage in half, right off the bat. Plus, it lets modern GPUs use their special hardware to go way faster. And the mixed part? We just keep a few really critical calculations in that high-precision 32-bit format to make sure everything stays stable. It's genius. Here's a great way to think about it. Full precision, or FP32, is like a massive, uncompressed, high-resolution photo. It's perfect, sure, but the file size is enormous. Mixed precision, or BF16, is like a really well-compressed photo. To you and me, it looks pretty much identical, but it's half the size. For training AI, this is the perfect trade-off. You get all the efficiency without a noticeable drop in quality. All right, next up we have batch size. This is literally just how much data you show the model at one time. Now, in a perfect world, you'd use a really big batch size. It makes the training process smoother and more stable. The problem? A big batch size can gobble up all your VRAM in a second. So, what's the workaround? Something called gradient accumulation. It's a super clever trick where you pretend to have a big batch. You process little chunks of data, one after another, add up all the learnings, and then update the model in one go. You get the stability of a big batch without the massive memory cost. This photo analogy really hits it home. Imagine you want one crystal clear photo, right? But your camera can only take these slightly blurry, low-res shots without crashing. So what do? You take, say, 8 of those blurry shots. You then stack them all on top of each other. All the little imperfections and the noise just kind of cancel each other out. And what you're left with is one sharp, high-quality image. That's exactly what gradient accumulation does for your model update. Okay, moving on to checkpointing and quantization. This is all about being way smarter with our memory management. So gradient checkpointing. This one is a real lifesaver. Okay, quick background. During training, a model does a forward pass to make a prediction and then a backward pass to learn from its errors. Now, for that backward pass, it usually needs to remember every single calculation it made on the way forward. As you can imagine, that eats up a ton of memory. Gradient checkpointing basically says, you know what, let's not do that. Instead of saving everything, let's just save a few key checkpoints along the way. If we need to know what happened between 2 checkpoints, we'll just quickly recalculate it. It's a trade, a little more compute time for a whole lot more memory. Let's stick with the photo editing analogy. The normal way is like applying 100 different filters to your picture. To make undo super fast, your computer saves a full preview after every single filter. Yeah, going back is instant, but your RAM just screams for mercy and fills up almost immediately. But with checkpointing, you apply the same 100 filters, but you're smarter about it. You only save a few key previews, maybe after the first filter, the 50th, and the 100th. Now, if you need to know what filter 75 looked like, the computer has to do a little bit of work. It has to recalculate from 50 up to 75. But look at the payoff. Your RAM is barely being used. It's a huge win for memory. And this chart shows you that trade-off perfectly. I mean, look at this. You might take a small hit on speed, maybe 20% slower, but you're getting a massive drop in VRAM usage, sometimes 50% or even more. For pretty much anyone training these models, that's a bargain you take every single day. It's often the difference between your project running or just crashing with an out-of-memory error. Okay, and our final lever is quantization. This is the most aggressive, the most extreme memory-saving technique we have. This is where we take those already smaller 16-bit numbers and we crush them down even further, to 8-bit or sometimes even 4-bit. The memory savings are dramatic. But this is the one that comes with a big warning label. There's a real risk here that you could actually start to hurt the model's performance. And this table really drives home a key point. A lot of the time, quantization isn't really a choice you make, it's a choice your hardware makes for you. I mean, look at this. If you're trying to fine-tune a 13 billion parameter model on a pretty standard 24-gigabyte GPU, you basically have to use 8-bit quantization. There's no other way it's going to fit. It becomes a simple necessity. So we know the 4 tools, but just having the tools isn't enough, right? Let's look at how a pro actually puts it all together. Okay, if you remember one thing, make it this sequence. This is the playbook. First, you always start with BF16 mixed precision. It's an easy win, a 2x memory save for almost no cost. Step 2, you play with your batch size and use gradient accumulation to max out your GPU without it crashing. Step 3, if you're still running out of memory, then you flip on gradient checkpointing. And only, and I mean only, as the absolute last resort, do you reach for quantization. You use it only when you have to because it's the one that can bite you back on quality. All right, we've been deep in the technical details. Let's pull back for a second and think about the big picture. And this really says it all, doesn't it? The real skill here isn't just knowing these tricks exist. It's about having the judgment to know which one to use, in what order, and crucially, when to stop. It's more of an art than a science. You're navigating trade-offs, not just checking boxes. Which leads us to the ultimate question we all have to grapple with. These huge general-purpose models from the big labs, they're getting scary good, and they're improving at a crazy pace. So you have to ask yourself, is all this work, all this effort to fine-tune your own specialist model still going to be worth it in 6 months, a year? The answer to that question is really going to shape what the future of AI looks like for all of us. Something to think about. Thanks for tuning in.